Welcome back to another video. Here, we will talk about why sampling is important in statistics. Statistical methods are used to make decisions and draw conclusions about populations. This aspect of statistics is generally called statistical inference. These techniques utilize the information in a sample for drawing conclusions about the population through parameter estimation, e.g., calculating means or proportions, and hypothesis testing, for example, deciding if observed differences are statistically significant. These techniques are fundamental in research, decision-making, and many practical applications. Remember that a population can be defined as a set of possible outcomes governed by a probability distribution, e.g., normal distribution, binomial distribution. Probability informs how samples behave given a population, while statistics uses sample data to infer population characteristics. When a sample is drawn from this population, probability theory helps us model and predict the behavior of these samples. For example, if we know that a population's heights follow a normal distribution with a mean of 170 centimeters and a standard deviation of 10 centimeters, probability helps estimate how likely it is to find a person taller than 180 centimeters in the sample. On the other hand, statistics is from sample to population. Statistics uses the data from the sample to make inferences about the larger population. It works in the reverse direction, taking sample information and generalizing it to the population. For example, if you measure the heights of 100 randomly selected individuals and find a sample mean of 171 centimeters, statistics helps you estimate the population mean and assess how accurate this estimate is. Using a sample, statistical methods like estimation and hypothesis testing infer properties of the population, for example, mean, variance, proportion. When studying a population, our goal is to either estimate population parameters, for example, mean, standard deviation, proportion, or test hypotheses about the population, for example, whether the mean, mu, is less than 40. Ideally, a census, collecting data from the entire population, provides complete information. However, conducting a census is often impractical due to constraints like time, cost, or the nature of the population, for example, infinite or continuously changing. Additionally, in cases where data collection involves destructive testing, for example, measuring the temperature at which a water heater explodes or the lifetime of a battery, testing every unit would destroy the entire population. As a result, we rely on sample data and statistical inference to draw conclusions about the population efficiently and without exhaustive or destructive data collection. The inference process begins with random sampling from a population, where a subset of individuals or items is selected randomly, in such a way that every member of the population has an equal chance of being included. This random sample is used to calculate sample statistics, for example, sample mean, sample standard deviation, which are numerical summaries of the sample data. These sample statistics serve as estimates for corresponding population parameters, for example, population mean, population standard deviation, providing insights about the larger population. The goal is to use the sample data to make informed conclusions or predictions about the population, relying on statistical methods that account for random variability and help ensure the estimates are as accurate and reliable as possible. Sampling techniques are methods used to select a subset of individuals or items from a larger population. Random sampling involves selecting individuals entirely by chance, ensuring every member of the population has an equal probability of being chosen, which helps minimize bias. Systematic sampling selects individuals at regular intervals from an ordered list, such as choosing every 10th person from a population, which is more efficient but may introduce bias if there's an underlying pattern in the population. Cluster sampling divides the population into smaller groups or clusters, for example, geographic areas or schools, and then a random sample of these clusters is selected, making it cost-effective for large populations, especially when they're spread out. Stratified random sampling involves dividing the population into subgroups, or strata, based on a specific characteristic, for example, age or income, and then randomly sampling from each stratum to ensure that all important subgroups are represented in the sample. Each technique has its advantages and is chosen based on factors like the nature of the population and the goals of the study. The story of the Literary Digest during the 1936 presidential election highlights a significant error in sampling. The magazine conducted a poll by randomly sampling its subscribers over the phone and predicted that Landon would win with 57%, while Roosevelt would receive 43%. However, the actual election results were the opposite. Roosevelt won with 62%, and Landon received only 38%. The fundamental mistake was selection bias, as the subscribers to the journal likely shared similar political views, skewing the results. Additionally, conducting the poll over the phone excluded a large portion of the population, particularly low-income individuals who were less likely to own phones. Another issue was non-response bias. Only 24% of those contacted responded, and those who did were more likely to have strong political opinions, while those less interested in the election were less likely to respond. This led to a skewed sample and ultimately inaccurate predictions. The lesson learned is that proper sampling methods and ensuring that the sample is representative of the entire population are crucial for accurate polling and decision-making. When estimating a population parameter with a single number derived from a sample, the best estimate would be the sample statistic that is most representative of the population. For example, if you want to estimate the population mean, the best estimate would be the sample mean. While it's almost never the case that the sample statistic will exactly equal the true population parameter due to random variation, the sample statistic provides the best estimate we can obtain from the sample data. It serves as the most reasonable approximation of the population parameter, even though there may be some error or uncertainty. This estimate becomes more reliable as the sample size increases, reducing the potential for sampling error. Similarly, best estimate population variance would be the sample variance, and best estimate for the population proportion would be the sample proportion. Sampling distributions refer to the probability distribution of a sample statistic, such as the sample mean x bar, sample standard deviation s, or sample proportion p bar, that is calculated from repeated random samples drawn from a population. Since each sample is randomly selected, each one will likely contain a different set of elements, leading to different values for the sample statistic each time. This variability means that sample statistics are themselves random variables, and just like other random variables, they have their own probability distribution. The sampling distribution is the distribution of these sample statistics, describing how the statistic would vary if we took many samples from the population. It allows us to understand the likelihood of different values for the sample statistic and is crucial for making inferences about the population from sample data. Please take a moment and think about the example shown here. Considering we have written numbers 1 to 100 on folded papers. Each time, we randomly pick 20 of these random numbers, read the numbers, and calculate the mean. We repeat this process for 40 times. Do you expect to calculate the same mean every time? If not, what does the histogram of these 40 means look like? What distribution does fit these data the best? Thank you for listening to this short lecture on why sampling is important in statistics.